Hello my dear students, in this lecture we are going to see divergence of a vector function and the physical significance of this divergence. Now already we have seen this introduction of divergence. Now see, let us say we have one vector A. If I consider vector A, let us say as axi plus ayj plus azk. This is vector A. Now similarly we have del operator. We have seen there is a del operator which is nothing but I cap dou x plus j cap dou y plus k cap dou z. This already we have seen, this del operator and vector, some random vector we have already seen, right? Now here divergence is defined only for vector quantity. In previous lectures we have seen gradient, and gradient was defined only for the scalar function, but here divergence is defined only for the vector function. Therefore for this A, let us say my vector function is A. Therefore I will say A is a vector function, any random vector function. Later we will see what is the real application in real life, right? Now my dear students, see the divergence, we have seen the definition of divergence. This divergence of vector A or divergence of vector A is nothing but del operator dot product vector A. Means it is a dot product. Divergence is a dot product. This is very important. This you must remember, right? And my dear students, also we have seen how to find this dot product. See, in case of dot product, there is a direct multiplication of coefficients and we have to add them, right? Multiply the coefficients and add all the multiplications. Therefore here this del dot A, both are here. This is a vector operator and A is a vector. Then it will become AX. See, with AX dou by dou X. You can write it as a first also. And see, dot product is always scalar quantity. Means this is a scalar. This is a scalar quantity. This you must remember. Right. Dot product is always scalar quantity. Therefore, I can write dou X of AX plus dou Y of AY plus dou z of az. See, it is also called curly x, curly upon curly x, curly upon curly y, curly upon curly z, or dou by dou x. It is also pronounced like this, right? Now this is the divergence, and my dear students, this divergence is always a scalar quantity. Means this is a one number. Here direct coefficients we are multiplying, that's why we will get number, right? And addition of all them. Now my dear students, let us understand what exactly divergence means, right? Now we have three types of divergence, that is positive divergence. We have three types of divergence, that is positive divergence, then zero divergence, and we have negative divergence. These are the basically the types of divergence, or we can say depending on the value of flux of particular field, we will say positive, negative and zero divergence. See, first of all we have to understand the, we have already seen the field, right? Now my dear students, for this field, if a strength of field increases, then it is positive divergence. If a strength of field is same constant, then it is zero divergence. And if a strength of this field decreases, then it is a negative divergence. Now my dear students, to represent strength, in previous lectures we have seen that if arrow length increases, then strength increases, and if arrow length decreases, strength decreases, and if arrow length remains same, the strength is same. So let us show positive divergence. Let us say we have one source. Let us say this is a source point from which there will be some field is coming out. Any field, this is a source for any field. It may be a velocity field, or it may be a electric field or magnetic field or gravitational field, any field, right? Now in general we are discussing here. Later we will see with the help of example. Now let us say from this source the field is coming, and let us say initially the length of field is this much. Here arrow length I am showing, right? This is the arrow length initially this is the arrow length of the field, right? Now my dear students, on the source we cannot define the divergence, or we cannot define the field also. on this source we cannot define the field, but the area surrounded by this field we can define the field, or area surrounded by this source we can define the field. Now see the length of arrow I have shown here. Now after some time, see, as I go away, the length of arrow is increasing like this. The length of arrow is increasing, and this is a representation. The length of arrow is now increasing, and this is a representation to show positive divergence. Means the strength of field is increasing here. The strength of field is increasing, therefore it is a positive divergence. We can say strength of field is increasing, therefore it is a positive divergence. Again, the positive divergence can be shown like this. Let us say if I consider one field like this, and as I go away, the length, see, as I go away, the length of arrow goes on increasing. Likewise, the length of arrow is increasing, right? This is called positive field. These both are positive fields. See, only the field or the strength of field must increase for the positive divergence. Now, for zero divergence, the length is constant. Let us say this is my field. Let us say this is my field. Now, if I check, the length will be always same. The length will be always same. Just a minute, I will show you. This will be the length. Now, if I consider more like this, if I consider more like this, see, length is always same. This is called zero field, right? This is called zero field. And for negative field, the length will decrease. Similarly, you can understand, initially the strength is more. For field, any field strength is more, then field, the strength goes on decreasing. As I go on, the strength goes on decreasing, right? The field strength goes on decreasing. This is called negative divergence. Now, my dear students, let us consider we have one positive charge. Let us say this is a positive charge. I will write as a plus q, right? Now, at this charge location, we cannot define the field. Already in the first lecture, in introduction to the field, we have defined that, we have seen that at the location of charge, we cannot define the field. Therefore, at the location of charge, we cannot define the divergence also, right? Now, but the area surrounded by this charge, we can define the divergence as well as field. Now, my dear students, from this charge, now is a source. This charge is a source of field. Therefore, if I define here divergence, now my dear students, for single charge, divergence of electric field is always zero. Means here, see the what I am saying, the charge will give the field in this direction. See, this should be the direction of field. Likewise, in all possible hemispherical direction or spherical directions, in all possible spherical direction, there will be a field. But here, the strength of field do not change. As I go away, the strength remains same. That's why here divergence of this electric field, here divergence means del dot electric field, divergence of this electric field is zero, and this is valid for point charge only. At a point charge only, at a point charge only. So my dear students, see, in coming lectures, in next lecture we are going to see Gauss theorem, and in this Gauss theorem we will see this del dot E is not zero. But my dear students, this Gauss theorem is not for point charge. If I apply Gauss theorem for point charge, I will get zero only. This Gauss theorem is for in general, but here I am discussing about the point charge only. If you don't know about Gauss theorem, don't worry, because in coming lectures we are going to understand and we are going to prove that Gauss theorem, right? Gauss theorem is applied in general, but we are discussing about the point charge only. Therefore, for any point charge, the strength of field is electric field is always same. That's why the divergence of this vector function or electric field is zero at a point charge. Similarly, if I have dipole, you might have learned about this dipole in your 11th standard. Dipole is nothing but one, there is a positive charge and other is a negative charge. We have one positive charge and other negative charge of same magnitude. Both charges of same magnitude, and distance between them is, let us say, 2a, right? Then it forms a dipole. This is called dipole. If the positive charge and negative charge of same magnitude are kept at some distance apart, then there is a dipole. It is called electric dipole. It is called electric dipole, and because of this dipole, there is a rotation of charge or there is a rotation of particle. Right. Now, my dear students, at this electric dipole, also the divergence is zero. This del dot E is equal to 0. Means for electric field, remember this thing. For electric field at point charge only and and at dipole, we can say at point charge and at dipole, and here simply I can write statement at point charge and at dipole. For an electric field, the divergence is 0. For the electric field, the divergence is 0. Again, my dear students, in a coming lectures, again in Gauss theorem, we will prove that the divergence of magnetic field is always 0. That is, the divergence of magnetic field, B is for magnetic, is always 0. It is always. Right. Where E is a electric field, E is a electric field, and B is a magnetic field. B is a magnetic field. Right. Now, my dear students, here in coming lectures, we will prove that in Gauss theorem, the divergence of electric field at a point as well as at a dipole is 0, but other condition it is not 0. But for magnetic field, the divergence is always 0. Always 0. And my dear students, such a field, such a field is called solenoid field. Such a field is called solenoidal field. Now, what is the meaning of solenoidal field? Solenoidal field means here the field in which divergence is always 0. Solenoidal field means the field, let me write the definition, the field in which divergence is always 0. Divergence is always 0. Therefore, here in example you can write for solenoidal field, magnetic field is a solenoidal field. Magnetic field is always solenoidal field because for magnetic field always the divergence is 0. Now, my dear students, after understanding the basic funda of divergence, let us understand the physical significance of divergence. So write down a heading, that is physical significance of divergence. Now, to understand this physical significance of divergence, we are going to consider a fluid velocity. See, consider a Cartesian coordinate system for a fluid flow. Now here, fluid flow means fluid is nothing but a substance which can flow. Fluid is nothing but the substance which can flow, such as liquids and gases are the fluids. Now what I will do, I will consider Cartesian coordinate. Cartesian coordinate means here 3D coordinates, right? Here I will consider 3D paralleloid. Here I will consider 3D parallelopipe, right? Means it is a 3D element. See how the 3D element is considered. It is a 3D paralleloid of volume. Let us consider the very small element I am considering here. Therefore, very small volume. This V is for volume. Here I am representing the horizontal line in V. Then think that it is a volume. And if I simply write V, then it is a velocity. Therefore, the volume is very small. The volume is, let us say, dx, dy, dz. Of very small volume, I am considering 3D paralleloid or 3D element. It is simply called 3D element. Now let us say the element is considered like this. Let us say the element is like this, and the dimensions are very small. With your eyes, you cannot see these dimensions. Right? These are the very small dimensions. Right? But here, for our understanding, for our analysis, I am drawing it by zooming it or enlarging by many lakhs of time. Right? Let us say this is the element. Now let us say this distance is dx. This is a dx, very small distance dx. Vertical distance I will assume as dy, very small distance dy, right? And here other dimension is dz. Let us this other dimension is dz. Now, my dear students, let me show the inside sides like this. You can imagine other sides also. And let us say this paralleloid. If I give here names, let us say corners A, B, C, D, then E, F, G, H. Likewise, I will give the corner names. These are our corners of the 3D element, very small element. Now let us consider the axis. Here I am assuming that vertical axis is a y-axis, right? And horizontal axis is a x-axis. You can give any names for the axis. And here perpendicular to x and y is z-axis. Means angle between xz is 90 degree, angle between xy is 90 degree, angle between yz is 90 degree. All are mutually perpendicular to each other. Likewise, you can understand on your notebook, horizontal is x-axis, vertical is y-axis, and perpendicular to your notebook towards you in the air is nothing but z-axis. Likewise, right? Now, my dear students, here let us consider. Here I am assuming the fluid flow means there will be a fluid velocity, and as it is a fluid flowing, the fluid can flow along x, y as well as z axis. Therefore, if I consider center of this 3D element, that is center of this paralleloid or mass center or centroid, it will be exactly at the center, right? Likewise, and from this center I am assuming that the velocity of fluid along x as vx, along y vy, along z as vz, right? Let us say velocity along x is vx, velocity along y is vy, and velocity along z vz, velocity along z is vz. And my dear students, this point is exactly at the center. This point is exactly at the center. Means if I project like this will be the line, and this line point will be here. Means here at distance dx by 2 from both sides. Both sides the distance is dx by 2, dx by 2. Likewise, you can understand. Both side distance is dy by 2, dy by 2. Both side distance is dz by 2, dz by 2. Exact center of your room. Means let us treat this as your room, and the exact center of your room, right, is nothing but this point, centroid in mechanics, right? Now, my dear students, here let us say velocity gradients. If I consider velocity gradients, means as a fluid is flowing, because of viscosity in the fluid, the velocity is changing. At location to location, velocity is different. Therefore, there will be a velocity gradient along x, y, z axis. Velocity gradient means, see, change in velocity in x direction with respect to x. Change in velocity x with respect to x is called velocity gradient along x-axis. Then similarly, change in velocity along y with respect to y, and change in velocity along z with respect to z is nothing but these are the velocity gradients. Velocity, we can say velocity gradients along x, y, and z axis. Means, see, if I travel by 1 unit, the velocity will change by this magnitude, right? Let us say if x is traveled with 1 unit, then change in velocity along x direction, right, will be dou vx divided by dou x. If I travel by 2 units, then it will multiply with 2. Means it is a rate of change of velocity with distance. It is a rate of change of velocity with distance. Means if x changes by some amount, velocity will change by this much amount, right? By this rate, velocity is changing along x direction. By this rate, velocity changing along y direction, and by this rate, velocity changing along z direction. These are called velocity gradients along x, y, and z. Right. Now, my dear students, already we know that the sign convention, towards right is positive x, towards left it is nothing but negative x, upward is positive y, downward is negative y, right? Towards you it is a positive z, away from you it is a negative z. They are mutually perpendicular to each other. These sign conventions I have to use here, right? Now, my dear students, let us do the calculation for x-axis, and the same calculation we will project on y-axis and z-axis. So here I have considered x-axis for our analysis. Then same results we will project on y and z-axis. Now let us find the velocity component on along x-axis on AHGD plane. Now if I write here the velocity at face, the velocity at face AHGD, which will be the inlet. This face is inlet, right? And here, because here flow is from along x-axis, flow is from left to right. Therefore, AHGD, this face will be inlet for the x, right? We can say for x, this will be inlet or inward, and this BEFC will be the outlet, or we can say outward or outlet, right? Therefore, the velocity along x at inlet, that is the velocity at face AHDH in x direction, this is for x direction only, will be equal to, see, here at center point there is a Vx, at center point there is a Vx, right? And my dear students, the rate of change of velocity with respect to x is dou v by dou x. This is a velocity gradient. Now see, from this point we are going backward by amount dx by 2. See, this distance, if I show with blue color, see this distance will be dx by 2, right? Because total is dx and this is the center point. Therefore, this distance will be dx by 2, means we are going back dx by 2, means it is a negative. And the rate of change is dou v by dou vx by dou x, and distance is dx by 2. Therefore, negative distance is there. Therefore, I have to write here minus, we are going back na, minus rate of change is dou vx by dou x, by this much rate velocity is changing, and if I multiply this rate with distance I will get total change. Therefore, into distance is dx by 2, right? This will be the velocity at phase ahgd, right, along x direction. Similarly, if I calculate the velocity on phase, see on phase this bcfe, right, similarly calculate the velocity along x-axis, at phase along x-axis at phase BEFC will be equal to, see at center velocity is Vx, at center velocity is Vx. Now we have to add the change, and see from center we are going towards right, means it is a positive distance, and by what magnitude we are going? We are going by dx magnitude, dx by 2 magnitude, right? This total is dx. Therefore, here we are going by magnitude dx by 2. Therefore, here towards right means positive. Rate of change is dou vx by dou x. This is the rate of change. And if this rate of change is multiplied with total distance, then I will get total change. Right. This is the velocity at phase BEFC along x direction. Now again one more thing, let us understand here. Let us say my dimensions are, I am considering one element like this, and velocity along x-axis we are assuming. Therefore, velocity is along x-axis. Let us say velocity is v. Right. This is a x dimension, vertical is y dimension, and this is z dimension. Now, my dear students, see for this element, what will be the volume? Volume of this element will be x, y, z. Right. And my dear students, this velocity is along x direction. Therefore, what we can write this velocity? Velocity is nothing but displacement. That is, displacement is along x direction divided by time. Right. This will be the velocity. Now, my dear students, if I multiply this velocity with a perpendicular area, let me show this area, this perpendicular area, that is yz. For x direction, perpendicular area is yz. Therefore, this velocity into area will become x by t into area is here y into z, which will become volume divided by time. X, y, z is volume. Therefore, this velocity into area is volume divided by time. This v is volume. This v is volume. This v is velocity. Right. Therefore, volume divided by time is meter cube per second. Volume divided by time is meter cube per second, which is called volume flow rate. This is also called volume flow rate. Therefore, whenever any velocity is multiplied with its perpendicular area, we will get volume flow rate. This concept you must understand, because here we are going to calculate the volume flow rate at inward or at inlet, and volume flow rate at outward or at outlet. And the difference of volume flow rate is very much important here, right? So I hope you understood this. The velocity along any direction into area perpendicular to the velocity is nothing but volume flow rate along that direction. And my dear students, here see scalar values I have written here, but in reality it is a dot product, because here we are looking for the divergence na. This is in reality velocity vector. Let me write here. In reality we can write it is a velocity vector dot product of area vector. Likewise we can write velocity vector into dot product of area vector, and as it is a dot product, then this volume flow rate is a scalar quantity. It is a volume flow rate, which is nothing but scalar quantity. It will be a scalar quantity, right? Because here velocity is a vector, area is a vector, and there is a dot product. Therefore, here I will write this statement. Write down with me. If velocity is multiplied with, if velocity is multiplied with area perpendicular to velocity, then we will get volume per unit time. Then we will get volume per unit time, volume per unit time, which is also called volume flow rate, called volume flow rate, or it is also called, it is also called flux. The same is called flux. So my dear students, remember here whenever any velocity is multiplied with its perpendicular area, then we will get volume flow rate, which is also called flux. So let us find here the inlet flux along x direction. Therefore, here inlet flux or inward flux at phase AHGD along x direction. We are calculating along x direction will be equal to, see, at phase AHGD velocity is here Vx minus dou Vx by dou x into dx by 2 into area will be, for this phase, let us show the area. Here I will highlight this area with red color. See, this perpendicular area will be there for this velocity, right? Which is nothing but, this area is nothing but here dz into dy into dz. Therefore, it is equal to Vx minus dou Vx by dou x into dx by 2. This is the velocity on phase AHGD into area is dy dz. Similarly, let us find outlet flux, right? Let us find outlet or also called exit or outward flux at phase BEFC. Let me highlight this area. See, this is the area. Yeah, this is the area. Now, my dear students, again there will be the velocity on this phase is Vx plus dou Vx by dou x into dx by 2 into area is dy into dz. Therefore, it will become Vx plus dou Vx by dou x into dx by 2 into area is dy dz. Right. Now, my dear students, this is the inlet flux and this is the outlet flux along x direction. Therefore, the difference of this will be the net outlet flux in y direction. Right. Therefore, here I will write the net outlet or outward, the net outlet or outward flux, the net outlet or outward flux in x direction will be equal to, see, here we have to write outlet flux at phase BEFC minus inlet flux. This difference we have to consider, right? So let us write down this difference. Therefore, what difference we will get? See, outlet is Vx plus dou Vx by dou x dx by 2 into dy dz minus inlet is Vx minus dou Vx by dou x into dx by 2 into dy dz, right? Now here can I consider dy dz common? Here this area can be considered as common, right? And here this Vx minus Vx will get cancelled and it will become 2 times, because minus minus will become plus. See, what I will do now, I will erase these velocities so that I will get sufficient space for the calculation, right? See what I am getting, this net outward flux, net outward flux along x direction, in x direction is equal to, see, Vx plus dou Vx by dou x dx by 2 minus Vx plus dou Vx by dou x dx by 2 into area considering common, dy dz. This area I am considering as a common, right? So my dear students, see here minus plus Vx minus Vx will get cancelled. In here, this half and this half will become 1, right? Half plus half will become 1. Therefore, the answer will be, see, this will become dou Vx by dou x into dx into dy dz. And my dear students, what is this dx dy dz? It is a volume of this element. This is the volume of this very small element, right? Now, let us find along, this is the net outward flux along x direction. Similarly, let us project the result on y direction and z direction. Therefore, here net outward flux in x direction will be equal to dou Vx by dou x, that is velocity gradient along x direction into volume dx dy dz. Similarly, the net outward flux along y direction. See, as here we have considered velocity gradient along x direction for x direction and volume will remain same. Therefore, for y direction we have to consider velocity gradient along y direction, which is nothing but dou Vy by dou y into volume dx dy dz. Similarly, if I write net outward flux along z direction, then I have to consider here as I am considering z direction, then I have to consider the velocity gradient along z direction. Therefore, it will become dou v z divided by dou z into volume dx dy dz. Right. Now, my dear students, these are the net fluxes along x, y, and z. Flux is nothing but volume flow rate. Right. Flux is nothing but volume flow rate. That is volume per unit time. Right. Now, here this is a scalar quantity. Na, we got velocity vector dot area vector. We got volume flow rate, that is flux, and dot product of two vectors is always scalar quantity. Therefore, here all the three quantities. Let me write here. This is the first quantity. This is the first quantity here. This is the second quantity, and this is the third quantity. All these three quantities are scalar only. Therefore, there will be a direct scalar addition. Therefore, here we can say the net outward flux, which is nothing but volume per unit time, outward flux through the 3D element, through this 3D element, right? Through this 3D element we called as parallelepiped, through parallelepiped, right? Will be equal to C summation of all these three, and in all these three, this volume dou x, dou y, dx, dy, dz is common. So let us consider this common. Therefore, it will become dou x of vx plus dou y of vy plus dou z of vz into volume, that is dx dy dz, right? This we will get. Now, my dear students, if I find net outward flux per unit volume, right? If I find net outward flux per unit volume, means divide this with volume. So the next step will be, for this I am dividing with volume, that is net outward flux per unit volume. Therefore, here we have to divide with volume, that is dx dy dz. Therefore, this dx dy dz volume will cancel from numerator and denominator. Then what we will get? We will get net outward flux per unit volume. Therefore, we can say the net outward flux per unit volume will be equal to, here we got dou by dou x vx plus dou by dou y vy plus dou by dou z vz. Now, my dear students, we have seen that we have two vectors, right? We have one vector, that is velocity vector. Velocity vector is nothing but vxi plus vyj plus vzk, and we have del operator. This del operator is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z. And if I consider dot product between them, this del operator is applied on the velocity vector, means we will get divergence. This is called divergence. So in dot product, there is a direct multiplication of the coefficients, na, and addition of them. Likewise, see dou by, which is nothing but dou by dou x is equal to dou by dou x into vx plus dou by dou y into vy plus dou by dou z into vz. Right? Direct multiplication of coefficients and addition. Right? And which we got as net volume flux per unit volume, net outward flux per unit volume. Therefore, my dear students, here the divergence, here the divergence, which is nothing but del operator on velocity. Here I am telling you significance of divergence. Divergence is nothing but flux per unit volume. Divergence is nothing but flux per unit volume. Now, depending on the quantity, we have to give the name of flux. Therefore, if this divergence is applied, if this divergence is taken for the magnetic field, divergence of magnetic field is a magnetic flux. It is a magnetic flux per unit volume. Per unit volume. So, my dear students, simply I can say divergence is a flux per unit volume. So, my dear students, simply write down the definition of divergence. See, here I am writing the at the end definition of divergence. Now, this divergence is defined as, it is a divergence is a net outward flux, net outward flux per unit volume, per unit volume applied, see, per unit volume over a closed surface, over a closed surface. This is the definition of divergence. And for any vector A, it is written as del dot vector A. and it is always scalar quantity because it is a dot product. Thank you, dear students. In next lecture, we will see some numericals on this divergence of a vector.